When we 3D print things, we load an STL or 3MF file into our slicer and we choose some settings based on what we've used before or what we understand, or maybe just a preset. And then we click Slice, and then we export to G-code one way or another. Now, my overall aim on this channel, or at least one of my aims, other than hitting 1 million subs and becoming literally the 3D printing channel, look, I've worked it out, it could happen, give me 100 years. Where was I? Oh yes, aim. My aim is to help you become better at joining the dots between all the parameters in the slicer and what literally gets extruded out of the other end. So with as few as possible further ados, well, just one actually, this is part of something bigger. The reason I was looking into this is because I have to use it for something I'm working on, which I kind of thought I was going to make a video about, but that's grown into a bigger thing, and this is like the 5th time I've tried to make a video and ended up canning it because it's kind of not turned out the way I want. Anyway, why not capitalize on what I've learned here and explain this? So, extrusion math. I'm going to use the word math throughout this video, even though the English word is not math. Most people who watch my videos appear to be American, so I'm just gonna, go with it. Extrusion math is literally everything to a FDM printer. All these machines do is they move in 3 directions and extrude molten goo, so when you're talking about extrusion math, from a pedantic point of view at least, you're talking about all the math. I don't really want to have to write a book on this, so I'm going to narrow it down a bit. I want to talk in this video about the relationships between the parameters you supply for width and height, and the nozzle size and line length, and the differences between infill and perimeters, and how that gets made into G-code statements. Should be simple, right? And importantly, I want to talk about the 2 most popular slicers, Cura and Prusa Slicer. I don't want to talk about any other slicers because I don't have a lot of experience with them. And I want to talk about the differences between how those 2 slicers do their extrusion math, because for 2 very similar looking programs, or at least 2 programs that do the same thing, they do have some fairly divergent maths going on under the hood. Now first up, I want to show you some G-code. G-code is astoundingly simple. I've shown it many times before and I've always explained what it's doing, but because this is a vast solid block of data, it looks more intimidating than it really is. If you ignore most of the parameter commands here, for example those that change attributes of the printer like the hot end temperature command here, once you pare it down, for 3D printers you usually just end up with a lot, and I mean a lot, of G1 commands. G1 means move while extrude, and the parameters this command accepts are straightforward too. You can supply any number of the parameters, so you can just supply X, Y, and Z coordinates, or just one of them, and you can supply an extruder position. The X, Y, and Z are the same coordinates that you're used to in the slicer, and the extruder is just an incremental value that relates to the millimeters of filament at the rollers of the extruder, at least if it's calibrated properly. There are some intricacies here, like absolute or relative mode, but that is beyond the scope of this chapter and probably a whole video of itself, and I'll probably do it in the future. All we need to know here is that every move that extrudes filament is just a move from wherever the nozzle is currently located to a given XYZ coordinate, and the printer will calculate exactly how to do that. There is one more parameter with the G1 command, which is the feed rate. Essentially, this equates to speed, but with the understanding that that also affects extrusion rate too, so the faster G1 moves will cause faster extrusion. You get the idea. Now of course it's time to break out the Play-Doh. What else would we do at this point in the video? The fundamental aim of a slicer is to convert a solid object into horizontal slicers, each made up of individual lines of extruded filament. Obviously. But the balance between the parameters you supply and the amount of filament supplied to the nozzle in those G-code commands is a calculation that the slicer does, and the slicer cannot afford to get that wrong. At all. The slicer must know exactly how much filament to extrude for each G1 G-code command. If you look at the G-code, it can seem like the numbers are a bit random, but of course it's not. It's really hard to understate how important this particular calculation is. Too much and you get over-extrusion, because more material has been pushed out of the nozzle than can fit in the line that it's occupying. Too little and you get a thin line, or you get intermittent lines, both of which are referred to as under-extrusion. All good so far, and I don't think there's any revelations at this point, but we have discovered that the amount of material extruded is literally one parameter, that E parameter. So how does that relate to line width and line height? Because we don't specify the flow rate in our slicer settings, not in that way anyway. We give height and width. So how does that work then? And I suppose a related question, what does nozzle size have to do with this? Tackling the first question first, this is the point where the real world hits the math and doesn't entirely meet. There are essentially 2 scenarios when extruding filament, at least that's the simple explanation. Scenario 1 is when you're extruding a line, say a perimeter or just a single line on its own, with no adjacent lines already present. Back to the Play-Doh and we can see, give or take, what will happen. The nozzle isn't just a single point that emits filament. If you look close up at a nozzle, you can see that there's a fairly large surface around the opening of the nozzle, and while I never really thought about it before, this must be somewhat intentional, because it acts as a constraint to the top surface of the extruded material, with of course the bed or the lower layer acting as a constraint for the bottom surface. With no side constraints, the extruded material will naturally form this kind of shape. The height we specified in the slicer is therefore just the height of the nozzle above the existing lower structure or the bed. The height is pretty reliable so long as the printer is working correctly. The width, however, is a dependent variable in this case, dependent on, I suppose, the viscosity of the molten PLA, in combination with the line height and the amount extruded. The short answer is it will form this shape, and so the width is kind of, I guess, it's approximate. When you're extruding with lines either side, though, you can see that the width parameter is easier to enforce. In fact, it's always enforced, as each consecutive line can be spaced by the movement of the nozzle, or, to put it another way, it's going to fit in there because it's the only squishy thing, so it doesn't get much choice. The second question, if you can still remember what that was, is easier to answer than the first. Nozzle size has almost nothing to do with the extruded line. Think about it. The G-code is specifying that, to give an example, a travel move of 20mm needs 5mm of filament extruding, all of which will be pushed through the nozzle. How much filament is extruded is constant, regardless of the size of the nozzle opening. The filament has nowhere else to go. This is why you may have noticed that you can print G-code that was generated for a larger nozzle size, and the odds are it won't go terribly. In fact, quite often it will print just fine. But that is not to say that nozzle size is irrelevant. I'll show you this Play-Doh scenario here. You can see this is pretty edge case for Play-Doh, and this will be analogous to, say, a 0.1mm layer height with a 0.6 nozzle, I guess. It can be done, and it would work, but it is definitely a better idea from an accuracy and finish perspective to use a nozzle appropriate to your line height, and for that matter, width. I'll put some recommended values on screen along with a link below to explain why this doesn't just mean you should always use a 0.8mm nozzle for everything. Of course, the page link does also point out that the nozzle size affects horizontal detail too, which makes sense. When you're drawing horizontal details with a large nozzle, it's kind of like if you had a fat marker pen and you're trying to write really small with it. Compared to a fine liner pen, you won't get good results. So far, we've avoided any math. If we carry on like this, it's going to look intentional, so it's about time for me to throw some equations in your general direction. Did you know that Cura calculates extrusion volume completely differently to Prusa Slicer? Me neither. I found this out by accident while I was looking into why layer height affects bed leveling, which was the can of worms that got me into the video in the first place. More on that later if I can ever actually complete that video, but if you want the single sentence version, layer height can affect bed leveling, but as things stand, you can level your bed to work well with all layer heights in the range of nozzle users, but more on that later because it's quite complicated. Exactly how the slicer works out this bit here is fascinating or terrifying, depending on how much you like equations. I'm going to zoom in on this so we can see what it looks like. Do you see it's basically like computer ribbon cable or a box of frozen crab sticks? It is halfway between fused together and cylinders, but it's not flat either. In theory, it would be a solid flat plate, and if you're obsessive over your first layer, you can just about make that happen, but that's, well, let's discuss that. Cura seems entirely unconcerned with the previous demonstration. Perhaps that's the best way, since in all my tests so far for the aforementioned video about line height, I have not managed to prove that it affects the results, at least on the first layer. To be clear, Cura's equation for the extrusion amount for single lines and infill lines is fundamentally the same. Height times width times length equals volume. Sound familiar? It's basically a rectangle. Cura sees all extrusions as rectangles. I haven't personally dug through the code, and oddly I'm not really inclined to, but there is enough documentation out there to more than slightly indicate that this is how Cura works. To quote the official documentation, the amount of material Cura engine commands the nozzle to extrude is equal to the volume of a box with the same length, width and depth as the line. That's what I just said. I mean, I imagine like most things there are exceptions to this, but that's what they've put in the documents, and importantly, the reason I know this in the first place is because I saw it when I was looking into the G-code during my previous video on bed calibration. Prusa Slicer, you may or may not know, was forked from Slickthrough in 2018 or whatever. I haven't really looked into the details, but that's the general gist of what happened. So Prusa Slicer's core logic, and I'm sure a lot more, is from Slicer. The equivalent flow math in Prusa Slicer is surprisingly more complicated. Not so much surprising that it's more complicated, I guess, but it's definitely surprising that it might not actually make a real-world difference. But I guess that remains to be seen. I'll link to the relevant pages in the description again, but the general overview is that Prusa Slicer sees extruded lines as the real shape that they are, or a good approximation, and treats them as a rectangle with two small circles, one at each end, like this. The area is therefore calculated as the area of those two parts added together, which I think is pretty clever, and therefore the volume is that cross-sectional area multiplied by the length of the extrusion. When you put two lines next to each other, Prusa Slicer also recognises that this isn't a perfect join, if you see our images from earlier, and it has an equation for that, which is obtained by subtracting the calculated cross-sections from a larger rectangle, but pushing them together. And it's a lot easier to see visually than mathematically, so I do suggest going no further than the images on this one. What's important to understand from the documentation, however, is that Prusa Slicer acknowledges that subsequent lines extruded next to existing lines is never likely to be perfect, which honestly points the finger squarely at Cura's math, does it not? As I hinted at already, I haven't been able to yet see a practical difference between the output of the two slicers with respect to this difference in logic, which honestly is surprising, but may be explained by one of the myriad parameters that each slicer has. To single out one piece of logic like this and try to compare is an interesting experiment, but it's likely to fail just simply because there's no way to have a control print sample. Both slicers work completely differently in some ways. Of course, we also have the global extrusion flow multiplier. In Prusa Slicer, I believe it defaults to 0.95. Cura runs at 100%. I mean, just that will make a big difference to the print. I don't really want to make this video too long, so that is all I wanted to cover of the theory at this point. But I do want to consider what this means for us in practice. How can we use this to influence our decisions as 3D printer operators rather than slicer software engineers? Well, honestly, I think that understanding how this stuff works under the hood allows you to make much more informed decisions about which layer height or width to use, or whether to swap nozzles, and how doing this will affect your output. It also allows you to rationalise some weird arguments that you might read on the internet, like how a nozzle that's worn flat would affect your print. I mean, given what we've just covered, I can't think that it will. It's more likely to work better as long as the hole in the centre hasn't changed. Something I do want to leave you to think about is vase mode. I want to cover this in the future, but you ought to now have enough information to be able to work out how you can improve the strength of items printed in vase mode dramatically in the same amount of time and at the same speed, but just changing one single setting. This is exactly what I mean here. When you know the theory, you can work out how to exploit it for better results, and if you know what I'm talking about, put it in the comments. So I hope this video was of some use. It's harder for me to make videos like this because of the burden of research, checking, probably still being wrong and then having to correct it. But if you do find this useful, then let me know and I will try and make more of this theory-based content in future. Thank you for watching.